Hello. Today we are going to talk about the second chapter of RCC, that is LSM Fundamentals, the theoretical. In this session, we are only going to cover the theory. So let's begin. What is limit state method? Firstly, for understanding what is limit state method, we should first know what does it mean when one says limit state. Basically, limit state is a condition just before the collapse of the structure. The structure may collapse due to bending failure, shear failure, compression failure, or maybe probably torsion. Also, Indian code says that a structure is also supposed to fail when it crosses certain serviceability limits. The examples of serviceability limits are deflection, cracking, vibration, etc. So let's bifurcate limit state method systematically first. Limit state is a condition just before collapse, as I have earlier stated. It is divided into two parts. First is limit state of collapse. The second one is limit state of service. Under collapse, there are four categories. A structure may fail due to flexure, as I said, shear, compression, or torsion. And under the limit state of service, a structure can fail due to deflection, cracking, and vibrations. This is the basic flow chart about limit state method, which one should remember, because in gate paper the question may be asked as in, for example, just to give you an example, they might ask which of the following is not limit state of collapse, and they might mention three among this and one among this. So you should know that okay, the one among this is the right answer because it is not under collapse. So let's go ahead. Now the first topic in our theoretical discussion is first we are going to consider load, and then we are going to consider strength of the structure. So let's start about load first. Load is the load which we use in our calculation while analyzing a structure is a design load. Now how to obtain design load? Design load is basically equal to a partial safety factor, let us say gamma, into the characteristic load. Now what is a characteristic load? A characteristic load is something which has 95% probability of not crossing that particular mark in the structure's entire life. That means that that value of load has 95% of probability of not being crossed. Only 5% chances in the entire life of the structure is that that value would cross. So that is characteristic load. And once we multiply that also with a partial safety factor, we will obtain a higher value, which is definitely far more less probable to surpass in the entire life of the structure. So this is what it means by characteristic load. Now this is the way to obtain design load. Now how are we going to? This is partial safety factor will be specified by the code. And how to obtain characteristic load? It's very simple. Characteristic load is basically, it is given by a formula which goes like this. Now one should understand that characteristic load, this is a technical term, is defined by upper bound here. The meaning of upper bound theorem is that whatever load you are actually getting in your calculations, you consider something higher than it. It's very obvious that load should be considered higher. If you consider less load and calculate the entire calculations and then design accordingly, then there is a risk of the failure of the structure. So the load has to be calculated to a higher extent. So that is the reason why we use upper bound theorem. Upper bound. That is the meaning of this theorem. Here F stands for characteristic load. Fm is the mean load. K is the factor. And S is standard deviation. We are going to do a few numericals based on this formula in our next session. For the theory purpose, just understand what are the terms specified in it. Mean will give you the average of all the loads which you have calculated, plus that is you are going to guess something more than the actual load. Mean is the actual load, but you are adding K into S. S is standard deviation, so that you are going to obtain a characteristic load value which is higher than the mean. So this was all about characteristic load. Now we will talk about another parameter, that is strength of the structure. Just like load, characteristic load, there is another term called as characteristic strength, which is denoted as FCK. And here the formula for calculating characteristic strength is this. And it's similar to upper bound theorem in characteristic load. In strength of the structure, there is lower bound theorem. The meaning of this theorem is, what it says is, whatever our mean strength of the structure or the particular member of the structure is, we consider little bit less. It's obvious that if you consider less strength than the actual strength, then you will have informal factor of safety, unofficial, non-technical factor of safety over your structure. So this will give you a psychological benefit to the structure. That is the reason why characteristic strength is calculated based on lower bound theorem. One should note that all the terms here are exactly the same as were in the characteristic load formula, except here it is characteristic strength. FCK stands for characteristic strength. This is mean strength. K is a multiplying constant factor, it's a factor, and here F is nothing but standard deviation. If we start speaking mathematically about characteristic load and characteristic strength, there are graphs under both the categories, which I am going to draw and explain you how to what you can say, how to make out what the graph is telling you, because it's a bit it's not a normal graph. There are no x, there is no y axis, and there is nothing mentioned even if you try to find out in the books, there is no mention of what the x axis stands for, what the y axis stands for. In fact, there is no mention of y axis in the book. So it is very important to understand this particular graph, because there is a possibility, and there have been certain circumstances wherein GATE paper has asked questions based on these graphs. So the conceptual understanding of these graphs is also essential. It's not much difficult. First, I will draw a graph related to characteristic load. I will make use of x and y axis, unlike it's mentioned in the textbooks. which will give you a better understanding of what is exactly told you in the test. Here the y-axis represents frequency and the x-axis represents load. Suppose the mean load of your member, which you are calculating in a structure, is say 30 kilonewton per meter. Suppose, let's assume this value. So let us mark 30 somewhere here. So before 30 it will be like 25, 20, 15, 10 and so on. After 30 it will be 35, 40, 45 and so on. Now if you check the frequency of the appearance of the load in for that particular member, if you carry out various experiments or various calculations to calculate the actual value of the load of the member, so there are chances of variations in the given answers. So those variations are being plotted as frequencies here. For example, if there are suppose 10 calculations done, 10 different calculations done, out of which 30 appears to be 3 times. So and it is the highest frequency as compared to all the other loads. So basically frequency will have a higher value at 30. And as it moves away from 30, the value of frequency is generally like this. It's like a bell-shaped structure. And since it is load, in load the formula for characteristic load was F is equal to Fm plus Ks. Now as I have said that 95% probability is there of that value not being crossed in the entire life of the structure. For 95% there is a value in mathematics derived for K, which is nothing but 1.645, or you can round it up to 1.65. For this 95%, 1.65 is the value. So whatever our characteristic load is, suppose 30 is the value of Fm, mean, it is the mean, that is the reason why it has the maximum frequency. So as you move ahead, the frequency decreases and we consider suppose 45 as our characteristic load. 45 as our characteristic load. So the distance here is basically K into S, which is this factor. If I substitute the value of K as 1.65 into S, standard deviations can be calculated by mathematical formulae, which we are going to see in the numerical sessions of this chapter. So this is the graph for characteristic load, and 45 comes out to be the value of your characteristic load. Please note that 30 was the average, which is the actual value, and you are considering load as 45, and you are going to later on design it for 45 so that your structure can support 45. If it is able to support 45, then definitely it is going to support 30. That is the whole and sole logic behind this formula. That is the reason why we use upper bound here. Now we are going to look at the graph for characteristic strength. Just like characteristic load, the graph of characteristic strength is identical. Only the upper bound theorem changes into lower bound theorem. I will show you, I will indicate you in the graph how does it change, how does it affect. The axes are exactly the same, just except for the x-axis. Here it is frequency only, and here instead of load, which was in the previous graph, it is strength. Similar to characteristic load, if you calculate the strength of, suppose you consider a M20 grade cube, so there is a high possibility of it attaining 20 Newton per mm square as its strength. So the frequency of the cube showing 20 will be high, and as you move away from 20, the frequency rate of the number of cubes reduces. So here also you get a bell-shaped graph. But unlike in characteristic load, we calculate characteristic strength by using lower bound theorem, that is minus Ks. Here also, as we have discussed in the earlier session, that characteristic strength is nothing but the strength which is also related to 95% of probability. Since in the previous graph, corresponding to 95%, the value of K was 1.645. Here also it is 1.645. So 20. So suppose, let us say this. This is the value. Suppose let it be 15. So for if you are getting 20 as the, I'm just giving you an example. If you are getting 20 as the mean of the various cubes which you have tested, and if you want to calculate the strength of your material, if you want to use it into the calculations of the analysis and design of the structure, then you interpret the strength of the material as M15 grade, because the Fm value may be 20, but after subtracting, the FCK value which you are getting is 50. So that is the reason why FCK value will be considered as 15 and the grade will be given as M15 grade. This was all about the terms which we were going to study in this particular chapter, that is LSM fundamentals. Apart from this, in this chapter, one important topic is on which there have appeared many times in GATE, many questions have been appeared in GATE, so that we are going to cover now. That topic is assumptions of limit state method. Alright, so the whole and sole reason why we are covering this particular assumptions is that not to by heart the assumptions, but to understand what is the meaning of those assumptions, what is the reason why such assumptions are made. For a lay person, if I were to explain a lay person, a fresher, a beginner of civil engineering branch, then I would say, if you would ask me what is assumptions, so I would say that assumptions are nothing but false statements made. Assumptions in practicality are never true, but they have to be assumed in order to reach a particular conclusion in a process. No assumption is 100% true at all. In fact, they are all the false statements. That is the reason why we assume things. Otherwise, we wouldn't have the need to assume those things because they were true. So assumptions are basically false statements, but they are. It is necessary to set certain assumptions. Otherwise, there will be a lot of confusions related to those assumptions. And if you assume a particular sets of conditions, then many of the doubts get solved in these assumptions only. Now, so let's begin with the assumptions. The first assumption was asked in GATE 2013 also, which was, it is called Bernoulli's assumptions, and it says that the strain distribution is linear in the cross section. with 0 at neutral axis and maximum at extreme fiber distance. This is the meaning of the assumption. What the actual statement of the assumption is that a plane section in a beam remains plane even after bending. I will just diagrammatically show you what it means. Suppose this is a beam. Alright. These are the supports of the beam. And if you consider a section which I am showing in red color, here it is. After bending, the beam will move like this. This is a bit exaggerated diagram of the deflection, but just in order to show you how the section moves, I am exaggerating the diagram. The deflections are not so high. So this red section over here in the black beam, when it is bent into the blue beam, becomes like this. The assumption is that this is plane. Now also it is plane after bending. It is not like this. It is plane only. It was earlier also plane. It is now also plane. It is not like this. That is the whole and sole reason of the assumption. What it means is, and this was the question in GATE 2013 paper asked for 1 mark. This assumption means strain, mind you, strain distribution is linear. We are going to make use of this assumption in the earlier in the coming chapters as well. So just understand the statement. Two key words are first is strain, the second one is linear. And the name of this assumption is Bernoulli's assumption. The second assumption is that steel takes care of all the tension in the member and not concrete. What does it mean? If you consider a beam cross section, a rectangular beam's cross section, there is a line which is called as the neutral axis. We will talk about neutral axis in a bit later part of in the coming sessions. But for the time being, you need to know only one point about neutral axis is that it lies somewhere around here in the center of the beam, around somewhere, not exactly in the center. The upper part of the beam takes care of the compression, and the lower part of the beam, lower part, the part below the neutral axis, this is the neutral axis, takes care of the tension. This is the only point which you need to understand right now for understanding the point which I am about to make. The concrete below the neutral axis does not take any it does not participate in taking care of any sort of tension. The whole and sole part of the beam which is responsible to take care of the tension is steel, which is somewhat like this. So the concrete is neglected. This is the second assumption. And the third assumption is that the maximum strain in concrete is one has to remember this value. This is 0.0035. This is the maximum strain which the concrete can take. We have to assume this, otherwise there will be numerous doubts in minds of many people. More than the students, the confusion will be amongst the scientists. Okay. Now this was all about the third point was all about the maximum strain which the concrete can take. Now what is the strain which the steel can take? The code specifies a particular sort of a expression which gives us the value of the strain, and I'm about to write the expression here. The expression goes something like this, and this is the value of the strain in steel, and this is an expression, not an equation. The strain should be greater than or equal to 0.002 plus 0.87 Fy on Px. The whole and sole reason for assuming this expression as the maximum value of strain in steel is the gradual failure of steel. Gradual means slowly, not sudden. So this was the fourth assumption in LSM, limit state method. So this is everything related to the theoretical part, except one last point which I would like to make, which is the bridge or the connecting link between the next chapter's theory. I would like to show you the link by drawing a graph. In SOM, you might have studied the stress-strain graph of mild steel. If you have, I will just make a rough sketch of the graph so that you might recollect what I am talking about. The x-axis is nothing but the strain, and the y-axis is nothing but the stress. The graph was something like this. Now you might recollect what I was talking about. Where this is the lower yield point, this is the upper yield point, this is the breaking point, and so on. This is the ultimate point, elastic limit, proportionality limit, and all. This was for mild steel. Now I am going to draw the same graph for concrete. Now one thing has to be understood, the graph which mild steel I had drawn, we have already done the experiment in order to obtain the graph, and we almost every time we obtain the similar sort of graph. But in case of concrete, the things are different. The graph of concrete is very complicated with respect to other graphs like that of mild steel. But in order to avoid all such complications, IS 456-2000 has given a separate graph for concrete, which I am about to draw. Also, one more point I would like to mention, which is very necessary to understand any graphs, not only this. The x-axis is the independent axis, whereas the y-axis is the dependent axis. When I say dependent axis, it means that whatever readings we take while performing that experiment are basically the y-axis readings, and whatever changes we make while performing the experiment is the x-axis. For example, if you remember how you made the graph for mild steel, then you must have observed that the stress is, you're not increasing the stress value. In fact, there is the graph here, it increases and suddenly drops. So basically, you're not increasing the stress value, you're increasing the strain. And while increasing the strain, whatever stress you are getting is basically the resisting stress offered by the steel. So x-axis is the dependent axis, whereas x-axis is the independent axis, whereas y-axis was the dependent axis. Now I'm going to draw the graph which IS code has given for concrete, the simplified version of the graph. This is the value of FCK for concrete. Now, one thing I would like to mention, and I would like you to listen very carefully. This is the most crucial part of the entire LSM. Many people study entire LSM and still do not know this point, why we have been using throughout the entire LSM. That is very important. That is the reason why it is very important, and can be asked for gate as well. Okay. This is the graph. Now, there is a term called as slenderness ratio, which is represented as lambda. Slenderness ratio is nothing but the ratio of the longer dimension, suppose the length of the beam, upon one of the cross-sectional dimensions, suppose say B, L upon B. This is the slenderness ratio. What it means is, as the slenderness value increases, the beam tends to become more slender, or probably I would use a word like the member. It can be a column as well. So the column or the beam or the member tends to be more slender. Slender means thin. The length is more, but the dimensions, cross-sectional dimensions are small. So more slender. As the slenderness ratio increases, the member tends to be more slender. Why I am mentioning this point particularly here? The reason why I am mentioning is the cube, the FCK value which we are obtaining from the cube test. It is basically 15 centimeter by 15 centimeter cube. But the concrete is not a manufactured product unlike steel. It has to be made on the site. Laborers are supposed to make it. So there is a chance of something wrong happening in concrete. Not the mixtures are not properly mixed. The components of the concrete are not properly mixed. Something or the other reason might be the reason why the strength of the concrete might reduce. So what happens is, as the concrete volume increases, or probably I would say the slenderness ratio increases, in comparison to the 15 centimeter by 15 centimeter cube, the volume of the beam or the column is very huge. So what happens is, the FCK value of the beam is less compared to what we get in the cube test. The reason for this, and it is also a question of gate, is the reason is the weak spots present within the concrete. As the number of weak spots, the size of the weak spots increases, the strength reduces. Now the reason the strength reduces is dependent upon the slenderness ratio. If the slenderness ratio, suppose I'm just giving you a brief idea. The slenderness ratio, suppose it is the value 2, and this is the FCK value. So the actual, this is the compressive strength. The actual FCK value for slenderness ratio 2 is not FCK but 0.8 times, a little bit less than FC. As you increase it, it becomes 0.75, more or less it tends to grow more lesser over the lesser side, and 4 it becomes 0.67. And experimentally it is proved that above the slenderness ratio 4, this value remains constant. So for a bigger member, we have to consider 0.67 FCK value rather than just considering FCK which we have obtained from the cube test. That is the reason why there is one more modification in this graph, which is 0.67 FCK. This is the elastic zone, while this is the plastic zone. This is the plastic zone. That is why I am making this line. The line, the stress after this is constant. Here it is constant. Here it is increasing. That is the reason why it is elastic. And also, I would like to mention the assumption in the IS code here is the strain value after which it moves from elastic to plastic state is 0.00, and this value, which was our, I think, second or third assumption, 0.00 for concrete. That's right. So this is the actual value which we should consider for a bigger members in comparison to a cube. Now we also apply a factor of safety which is 1.5 for concrete, which makes the graph 0.67. If you use the calculator and divide 0.67 FCK by 1.5, you are going to get a value 0.45 FCK. So this is the graph which we get, and what the this is the final, the black graph, the lower one, this graph is the one which we actually use in our design calculations in LSM in general, and that is the reason why 0.45 FCK is used. The importance of this 0.45 FCK, you will realize, both of us will realize in the later parts of the topic, that is the subject. And this graph, since it has elastic and plastic zone both, it is also called as elastoplastic graph. So that is everything related to the theoretical part of LSM fundamentals. This completes the theory part. In the next session, we will take some general numericals related to this topic, and later in the another session we are going to take the gate questions related to the same. Thank you.